Okay, so let's begin. So welcome, England. So he'll talk about parametric linear system solving with error correction.
Okay, thank you. Good afternoon. My name is Waddell. I'm a recent graduate of NC State. So today I'm going to talk about more or less the work I did for my dissertation. This is work with my advisor, Eric Kaltofen. Some of the earlier work is also work with Clement Pernet and Arne Stroyohan. So currently I'm a visiting faculty at the Evergreen State College out in Olympia. It's an honor to be here at CUNY. I'm actually a graduate of CUNY. I have an associate's degree at Medgar College in Computer Science and a BA degree from the CUNY baccalaureate program, which I think is on this floor.
So did you know Alexei before?
Not from CUNY,
Yeah.
but we met at a conference or two.
I see.
I did take one class at Queen's College though, but not with Alexei. That was differential equations. All right, so first I'm going to talk about error correction and then the parametric linear system solving. And then I try to connect these two ideas together. Now, error correction is a broad field. I'm going to talk about a very small portion, in particular, Reed-Solomon codes, and even more particular, the Gemelle-Sudan view of Welch-Berlekamp decoding of Reed-Solomon codes. Then I'm going to talk to you about an early termination algorithm for this Boyer-Kaltofen algorithm for solving these parametric linear systems. The other thing is that solving these parametric systems can be specialized to recovering a vector of rational functions from their evaluations. So we'll talk about that specialization. So another thing we'll talk about is, so error correcting codes is usually used for, you have a network, I'm sending something across a network, and I want to be able to recover what I sent. Now, what's interesting is recovering a vector of polynomials is very similar to what is known in information theory as, can be sort of viewed as a burst error correcting code, or interleaved Reed-Solomon codes. So I'm going to describe that problem, and I'll give a model for the polynomial recovery as a burst error correcting code, as well as a model for testing, a channel model for testing how well this code does on this particular channel, burst error producing channel. Then finally, I'm going to talk about doing the same, solving these parametric systems when the matrix of the system is rank deficient. So the assumption I'll make in the beginning is that the matrix we're working with is full rank. And it turns out that it doesn't carry through for rank deficient systems. We have to make some adjustments, and I'll talk about that. And then I'll talk about some future direction of the work, and that will be it. All right, so an error correcting code is this idea of adding redundant and parity data to a message you wish to send over a network so that it may be recovered. The codes we're going to be dealing with are all linear codes. And by linear codes, we mean that any linear combination of the code words, and the code words, that is the message plus the redundant data. Any linear combination of code words will give you a new code word. And block codes are codes that are of fixed length. So we'll be dealing in that area. So again, the idea is I have a code word, I'm sending it across a network, something happens, and I get a received word. Something may happen. It's possible that the received word is not exactly the code word that was sent. Under certain circumstances, we're able to recover the code word. So, a simple example of how we will view Reed-Solomon codes. So, the first thing we'll do is you construct a polynomial f right? Where the coefficients of the polynomial are, it is the message you want to send, right? Now, we'll have a bound E on a number of times where, or a number of places where the received word differs from the code word. That's our bound E. And the number of evaluation points is determined by the degree of F plus 2E plus 1. Those number of evaluation points we're going to need in order to recover the code word, as long as no more than E errors occur. Now the code word will actually be the polynomial evaluated at those L distinct points. So if our message is 1 to 1, so you have a polynomial U squared plus 2U plus 1, and the idea is using our formula for L, we pick 7 distinct points, and our code word is the evaluation of the polynomial at those 7 distinct points. And so let's say the received word is beta. Notice in one place the received word is not the same as the code word, but here E is 2, right? Because the F is 2, 2E, 4, did I do it right there? 4, 6, 2E plus 1. So anyways, for the code word has capacity to correct at least 2 errors, and so if this were the received word, we'd be able to recover the polynomial. And remember, the coefficient of the polynomial is the message that we wanted to send. Okay, so how do we do the decoding? Well, first you define a polynomial lambda. So this is the Mills-Sudan view of the Welch-Broadcom decoding algorithm. So you define a polynomial lambda. A lambda is such that at any place where an error occurs, this is a root of lambda. So then you set up this equation, beta. Remember, beta is the received word. Beta times lambda equals F times lambda. And this is true for all evaluation points xi sub L. Because if there's an error, lambda is 0. And if there's no error, beta is the same as F. Then the idea is you create these generic polynomials, phi and psi, where the degree of phi is the degree of F plus E, and the degree of psi is E. And then you solve linear system beta times psi equals phi for the coefficients of phi and psi. And this equation is linear in the coefficients of phi and psi. And if you just do phi divided by psi, you get back F. So that's this Mills-Sudan view of decoding Reed-Solomon.
What's the standard view?
Say again?
What's the standard view before Gamel and Sudan? You said this is a Gamel-Sudan view.
Yes.
What was the, let's say the...
So usually
how is it usually presented?
So usually you don't think of it as a polynomial. You use finite fields, and so you don't usually view the Reed-Solomon code as the coefficients of a polynomial. Usually it's you have a finite field, and it's let me think about that. Yeah, because actually I'm saying that wrong. Because originally it was equivalent to the polynomial. I'll have to think about it.
I think traditionally, yeah, you always think of a finite field with F vectors in F, right?
Yeah.
And much more concrete. Now you're doing more algebraically, so it's a little bit different.
Because I actually think why I stopped short, because I think originally the Reed-Solomon code was decoded this way, where you set up these large systems and they do multiple checks. And then the ones that was more common was the way they would decode it. To be honest, I'd have to go back and look at how the original way did, because this is not how because Welch and Berlekamp, they designed the system to decode read-Solomon code. I mean, it's a patent that they had in 1986, which have shift registers and these kind of things. The way they looked at it. But this is just an algebraic, yeah.
Right.
All right. So now I'll define what we mean by parametric linear systems. So for the parametric system, we assume we have a matrix A and a right side vector B. And we'll assume that A has full column rank and and the system is consistent, right?
Where's the parameter?
So the coefficient, the entries of A are polynomials in U and B.
So U is the parameter.
Huh?
U is the parameter.
U is the parameter.
Yeah.
Only one parameter.
Yes, one parameter. And what we want to do is we want to solve for the solution. And the solution we're looking for is the solution with the common denominator G. This is a rational function vector, where you have the common denominator. And the GCD of the polynomials is 1, between F and G.
And those are derivatives after the I?
No. So we use this notation because so I is the position in the vector.
I see.
Because usually F sub I is the U sub I, U super I.
Okay.
So we use this bracket for the position.
Mm-hmm.
All right. So so the idea is you have a black box, and you can consider that the black box contains the linear system. And what you can do is you can probe the black box, and in output you get scalar systems A hat and B hat. But A hat and B hat are not necessarily the evaluation of A and B, right? Because if it were, you could then just interpolate A and interpolate B. But here, will you guarantee that? Should go to the next. Will you guarantee this though that fewer than E times you get a scalar system such that the evaluated solution does not agree with the scalar system? And those evaluations we'll consider to be errors. So you get these scalar system A hat and B hat, and most of the time, if I were to have the evaluated solution to the system for the point that I probed at, A hat times F will be equal to G times B hat. But sometimes I get systems such that A hat times F is not B hat times G times B hat. But no more than E times of this occur. And we still want to recover the solution X for A and B. And so what we show is, so as generalized form of the Welch-Berlekamp algorithm works for resolving this problem. And here R is a count on the number of times the matrix drops rank. Then we show another count due to work by Stanley Kabai that also you can use to recover the solution. Where here D sub A is the degree of the largest polynomial in A, and D sub B is the degree of the largest polynomial in the vector B.
Do you mind showing the previous slide?
Yes.
Would you again explain the counts? So what do they do?
So there's a number of number of probes. So you need, what is the least number of requests to the black box you would need? Yeah.
In order to
To recover
F.
X. Yeah, F and G.
G.
Yes.
And what's lambda again?
Lambda is the error locator polynomial. So lambda is such that if you were to find the roots of lambda, those would be exactly the places that where the received word is not the same as or exactly those places where xi sub lambda a hat times f is not g times b. I guess what I could say. So usually, okay, I know I left that slide off, but usually with error correcting codes, you don't really care where the errors are. You just want to recover the polynomial that you sent, the message. But if you were to take the lowest degree psi from the solution, that's lambda. That's the error locator polynomial. And so the same thing here. If you take the lowest degree psi, that is also and you take the common factors between phi and psi, that is the error locator polynomial. But that sort of work that was done this is why I sort of didn't put it here, by Boyer-Kalterman. So one of the things we did though was, so in trying to recover f and g, you need these degree bounds. Degree bound for the numerator of the polynomial, a degree bound for the denominator, and sometimes a degree bound for the matrix and right side vector. But because these are degree bounds, it's quite possible that these bounds are very large, or way too large than the actual degrees. So what we show is what you can actually do is start off with a lower count and increment until you reach the degree bounds. Right. So what happens is, so you can start with an initial L, the amount of evaluations you want to use, and then you try different values for df star and dg star in this new count, lbk star. And what the algorithm will return to you is whether or not you've actually surpassed the degree of f and the degree of g. If you haven't, then you can increase L and then retry values for df star and the g star. And the algorithm will terminate exactly when you've surpassed those bounds.
But if those degrees originally were very high, maybe it will take too long to get there. Will it be faster just to start from the bound? Have you seen examples in which it's better just to start from the top rather than going incrementally? So
actually, yes, I mean with the small examples that we used, yes. I mean, you could always, right, just say you have this large bound and use that, right?
Would that be faster actually than going incrementally?
Would it be fast? I mean, I could imagine some cases in which they are, but I would like to think if you were to have a random system, it would be faster to do this.
Okay.
If you have very little information about the degree bounds.
So, so you're trying all D star F and all D star G?
That fit the count. You have a count E and you have a count R. Well, you can assume you have that. Maybe you also have a way to be based on the number of evaluation points. Because the other thing is too, also left off here, but you might have what is called an error rate, right? For your black box, based on the number of evaluations you give to the black box, that could determine how many errors that are likely to occur. So the more
right, but let's
probes,
stick to this model,
yes.
right? So I try it. How do I know whether my degree is right or wrong?
Yeah, so that's sort of. So what we prove is that you cannot be fooled by the the F and G you receive, right? So this is now
you get an F and G back.
yes.
And then you use to check whether F and G is good.
Yes.
For your, and you know whether it's good or bad.
Yes.
And if it's good, you're done.
Yes.
It's not good, you increment.
Yes.
I see.
And similar process for the compiled count. Right. So now the other thing we showed was, okay, maybe the problem is I have a vector of rational functions in the form f over g, where the GCD of the f's and the g, then there's no common factor between the f's and the g. Well, among the polynomials, all of the polynomials. And I want to recover the rational function by probing the black box. And again, we'll assume that no more than e times will I receive a vector where in some place beta is not the same as gamma, right? Gamma is the evaluations of f over g. And the idea here is, well, you can consider A to be the identity, A hat to be the identity matrix, and B to be this vector, to be the vector that you get back from the black box. And at places where you have a pole, and by pole we mean where the denominator is 0, you just return the equation psi equals 0. Because remember, it didn't matter what A hat and B hat you had in order to recover f and g, right? So that's why you can let A hat, if the matrix were square, you can let A hat be the identity matrix and B hat just be what I get back from the vector, and use that to recover the vector of rational functions. And what that allows us is then to use the properties we get from our polynomial system solving to get a degree bound on an estimate on how much points I need to recover the vector of rational functions. So one of the things that we showed is that, well, this bound, the Broadcamp bound for recovering a polynomial is actually tight. If you were to try to use one fewer evaluation point, you can always construct a second solution.
What do you mean by all the characteristics of the original solution?
So the degree, the fact that, so the degree of the polynomial, the degree of the denominator, how many errors are in the solution. So in some sense, you have a solution that you cannot distinguish from the original solution, if you were to use one few point. Now the thing is,
do we care? What do we care?
Because I mean, if it were just a polynomial, yeah, because then you'd think that you got the message, whereas it's a different message.
Oh, I see.
But what I should say here though is, and what other folks do is that, well, if the errors are random, with a high probability you will get the correct solution with fewer evaluations, and that's stuff. For instance, in list decoding and other methods people use to show that with some high probability. But what we show here is that if you have fewer points, right, then the Welch-Broadcamp count is tight, because you can always, there is another solution that looks just like the original solution. But that's in the case if I just have one rational function. However, for the vector case, you can do better than the Welch-Brodelkamp count. And so let's say we have exact degrees, we don't have degree bounds anymore. Then this LCAP count is less than the LBK count every time the degree of A is less than the degree of G, the denominator. All right? So it turns out that you can actually save evaluations when you're trying to recover a vector of rational functions. Then, use field evaluation and this generalized Welch-Brodelkamp count. Now, the other thing is, now you might think, well, if I wanted to get fewer evaluations, then what I could then do is just repeat the polynomial several times, or the rational function several times in the vector to try to beat the Welch-Brodelkamp count that way. But it turns out you can't, because if the polynomials are the same, if the numerators are the same, it's always the case that the degree of G is less than the degree of A. So you cannot just beat the count by repeating the vector. Right. So now I'm going to switch gears a little bit. And now we're going to consider recovering a vector of polynomials. Because what we want to do is we actually want to think about our work as a method of sending data over a network, right? Because with the rational function case, the denominator, that's just wasted values. You sort of can't construct the message that way. So we'll consider
why is a rational function wasted?
So if I want to send data over a network.
So I'm still not very clear about the framework. So you're trying to send a message, and the message is F.
So that's not what we're doing
in this case.
In this case, what we're going to do.
Oh,
before we're just solving the parametric system.
So
using this idea of error correcting codes.
We're solving the system of
the system AX equal B without access to A and B. And the solution is a rational function vector.
That's the original problem.
Yes.
And in that framework, what is the message and what is the...
So there's no message there. We're just recovering the vector.
But technically, F is the message, right?
Yes. This is what I'm going to do now. Is I'll consider these Fs as messages I want to send over a network.
Okay.
And
previously, it was only single F.
No. Well, in terms of the message, yes.
Okay.
There's a vector of polynomials.
Yeah. Before it was a vector of
solution vector.
Previously?
Yeah. Because there was a system. In that system, each matrix entry was a polynomial.
Right.
So you solve it, you get a vector with entries that are polynomials.
Vector will a rational function.
Rational functions, yes, rational functions.
Okay.
So it was a vector of rational functions.
Yes.
So here is a vector of polynomials.
Yes. Because here we actually wanted to think about sending message over a network. So there was just solving a linear system.
So he's changing the question.
Yes.
He's answering a different question now.
Right, in that framework, you're trying to just solve equations.
Yes.
So there is A and B.
Yes.
Here, there will be A and B showing up, right?
Yes.
And the A and B in this framework is what?
He hasn't, he didn't say.
Right, okay, I'll let you go first.
All right. So we I guess I should put it this way. What we want to do is use some of the information we gathered from the rational function vector recovery problem, and use that to message in a data transmission setting. So here, we'll assume we have a vector of polynomials, and we'll assume that when something goes wrong, everything in the vector is affected, right, for now. So before the assumption and the error was that an error meant someplace beta and gamma or f over g are not the same. Here we'll assume error means that every position in the vector is affected.
So where's the A in?
So there'll be no A and B here.
There's no A.
Because what we showed is that you really don't need A and B to recover the vector of rational functions.
But what is the sign and beta?
Although you can.
Evaluating.
So yeah, this is evaluating the vector of polynomials, and beta is the value you get back from the field K.
So somebody's giving it to you. There is a system there.
Yes. Well, of this black box system, right?
So there is a black box again.
Yeah.
And you get to choose the sign. You're evaluating a sign, right?
Yes. And so what we show here is that with this scenario, if you assume that when an error occurs, that the error occurs affects every element in the vector, that you can solve a smaller system than usually you set up these systems in phi and psi, where phi is this degree of f plus 2e plus 1 many points, and psi is degree of, well here psi is degree of g is actually 0. But what we show is that you could actually from all but, so I'll show next. And what we were able to do is remove this assumption that you needed the errors to be random, right? In order to solve a smaller system, in order to reduce the number of evaluations you actually need to, essentially not evaluation points, but the size of this system, the linear system that you set up, can be much smaller.
So all this is still in finite fields, right? The psi and so on.
Well, so we don't make an assumption on the size of the field.
Yeah, but it's
It could-
when you're trying to evaluate it, or
Yeah.
you have to choose a field.
Yes. But I'm saying, so we don't assume that this field is finite. But if the field is finite, you'd have to have enough points in the field
Right.
to make the assumption.
Sure. So, okay, so you're saying you don't care whether the field is finite or not, right? Is that right?
Yes. Here, in Black and Beck, they do use a finite field, and they say with this probability, if the errors are random, that you can solve the smaller system and recover the solution. What we say is, well, we actually don't need to make an assumption in the field. We actually don't need that the errors be random. If we assume that the errors affect the entire vector.
How can you assume? Maybe accidentally they might.
Okay, so we'll go through that. That's just the beginning assumption to sort of set up what I want to set up next. So this is the system that you originally solved. This is when you solve this linear system in phi and psi, right? And so this is depending on how many polynomials you have. These are these van der Waals systems. And what you can do is you can remove E evaluations from every system except the first one. Reduce the size of the system. And what we claim is when you solve the system, you can recover the polynomial vector. So now we're going to consider this in the data transmission setting, right? So F1, F2, and Fm, these are all messages I want to send across a network, right? And now what you could do, so the idea is you're sending the evaluations of the polynomials across a network in sequence. And it's possible that
Evaluations of
yes, of F1 at x0 and F1 at fx1. These are remember the code word is the evaluations of the polynomial.
evaluation at what? You can choose.
Yeah,
points.
the points, yeah, that you choose, yeah. But here you know the degree of f. So degree of f plus, you have some bound on how many places you think, how many times you think you will get an error. But the assumption here will be that when an error occurs, it will occur in a burst. It could be maybe, something happens that causes a string of errors to occur.
Seems very strong, right? An assumption that.
I think that's probably a better assumption than the error occurs at random. So you're sending something over a network, and maybe a thunderstorm is happening or something, and now I get a string of errors, or some disruption happens. So the idea is if an error occurs at a point, then with high probability the next evaluation point is also an error. That's the assumption for burst error correcting codes. So the issue is, if you were to send the messages this way, it could possibly, each of the Reed-Solomon codes have a capacity for a number of errors they can handle. But if it occurs in burst, you might have it so that too many errors occur in just one of the Reed-Solomon codes. So what you want to do, and this is what they term interleave code, is actually send them interleave. Consider not sending one polynomial at a time, but if you're sending the vector. So you send f1 at x0 and f2, and send it this way, so that you can somehow distribute the burst errors among the polynomials. And this is termed interleaved Reed-Solomon code, and this gives you a better chance of recovering these burst errors. So what we're going to do is we're actually going to set up a model for a burst producing channel. And how this channel works is you're either in a good state or in a bad state, right? If you're in a good state, this means that no error occurs. If you're in a bad state, errors occur. And you have some probability that you either remain in a particular state or transition, right? And with this model, you can compute stuff like the channel burst length, the symbol error rate, what is the mean number of bursts you expect. All right, so this is the setup. I have a vector of polynomials. I have 4 polynomials that I want to send over the network, right? And what we claim is that if errors occur in bursts, and by burst we just mean that it affects the entire vector, and we claim that we could reduce the number of evaluations we need, and we remove them from all but one of the polynomials. So in this example, E is 4, so I should be able to remove 4 evaluations from every Reed-Solomon code, right? And the claim is I should still be able to recover. However, in the data transmission setting, remember we're sending the message this way. First we send it this way, then this one. The problem is you have this 4 extra in the tail, and if errors occur at the end, maybe too many errors will be in the first polynomial. So then we just shift our interleave this way. So that you have maximum separation between any particular read-Solomon code. Right. So let's just say that you have a burst, the average burst length is 3. You have a burst length, well, it sort of depends on where the bursts start. If the burst starts on the top, you're good. Because in some sense, you could think of it as this complete read-Solomon code word finds the error, and so you get these 2 errors for free. But then if the code word starts here, you get nothing here, but then sort of, you can discover this one from the complete read-Solomon code word. Or if the error might start in the bottom, this is the complete words, you get this error for free, and you need an extra evaluation to find this one. So, in order to get more things for free, you move the complete read-Solomon code word to the center. All right. So the idea is, another thing you might be able to do is, you're sending a large message, so maybe you have multiple of these systems that you're going to send. Rather than sending them one at a time, you can somehow double interleave your system. Right? Just set up you can consider these individual blocks to be your code words, and interleave again. So now you can recover longer bursts within this block. Because if an error occurs and it affects the red portions, then you will recover the polynomials, the other polynomials in that block, in that column.
That doesn't, it's very strange to me. I mean, you can keep repeating this process, right? I mean, I can break it up again and shuffle again and things like that. So what is going on here?
Well, I'll hopefully...
I mean, you're doing it twice, right?
Yes. Well, so
twice.
So the idea is that maybe I should go to this slide here. I'm probably running out of time, but so the idea here is, all right, let me explain these 2 tables. So remember, you can somehow, based on the channel that you might have, you might have some information on what you think the average burst length is, right? You might have some information on how many errors you think are going to occur, right? And so what you could do is you could send one, like you said, it could be just one complete system. The problem with that is, I think sort of what you alluded to earlier, it's a bad assumption that when an error occurs, it will affect the entire vector, especially in the transmission model, because I don't know where the errors are going to occur. So if I just had this, if I would just send it this way, and this was the only red value, I'd need my burst to at least be 1, 2, 3, 4, 5 long to correct. But with this setup, I could correct bursts that are 3 long, or 5 long, or 6 long. The bad ones will be the ones that are that are only have length 2 and occur in between here, because the complete read-Solomon code word didn't see that. So that's why you want to do the double interleave. So part of what we were doing is sort of experimenting between the 2 setups, right? Here, by stack I mean whether or not I do this. And by not stack, I just send them this way. One block at a time, right? Not burst only, what I mean here is that I consider that I could have both burst errors and non-burst errors. Errors that occur in some succession, and maybe sometimes I just get random errors at one point, right? Or those errors that do not actually affect the complete read-Solomon code work. That's what I mean by a non-burst error. And by the non-minimal interleave is, well, actually, for this system, 3 is the minimum you can do. You cannot have an interleave depth of 2. That wouldn't work, right? So the smallest you can have is 3. So maybe you want to just use the minimal. So we actually tested all of them. I only included these 2. But preliminary results, you can see that if you were to stack it, you do better in correcting, right? So what this is, you set up this system, right? And I imagine that I do 100 of these messages, right? And I let the errors occur based on the Gilbert channel. And I see how many times what my system produces is actually the polynomial vector that that was in the black box, you can say. So I have a polynomial vector, right? And I evaluate it at some points. I let the errors be determined based on the Gilbert channel where errors occur. Usually you'll get burst errors, so you can see this somewhat with the burst lengths. And then I check to see how many times what I recover is exactly the polynomial that I started with, the polynomial vector that I started with. And you can see that if I stack them, I recover a lot more than when I don't. And these are varying values for the probability that I change states. And so then what the idea is that then you can then try different things, right? You can try using only the minimal interleave and see if that would be better, right? And then the other thing is to see, well, this is the code length as compared to the actual message length. So what we sort of did is we set up this framework where you can then test these results. And what would be interesting is to see how this compares to, in some sense, the standard view of interleaved read-Solomon codes. Because it is known that if you have interleaved codes, you do recover better. You do recover burst errors better, or your error correction capacity grows. What time is it? So,
what you're saying here is that kind of the strategy for interleaving these polynomials kind of allows you to do fewer evaluations. Is it?
Yes. Yes. Because if I were to just use the original idea and then send complete codes across a network, right? That would just
So the part I'm not understanding is like the errors. So somehow this strategy works because the errors occur in clusters.
yes.
Say again for me how it works.
Yeah. Okay. So I guess our improvement, like you said, is sending fewer data points across the network. Where we just, before we send anything, we say, well, if for the most part error occur in bursts, I actually don't need these extra evaluations. If you were to send those extra evaluations and your degree and no more than E many errors occur, you'd always recover. That part, But we want to say, well, maybe it will be more efficient to just send fewer. If for the high probability you can still recover. Now, why the interleaving is better is if you were sending, that was this slide. Go back a little bit. Here, right? If you send the polynomial this way, remember each read-Solomon code has some capacity, right? And maybe the capacity of each one of them is 4 errors they can handle, and an error occur that is of length 6. and they all occur in the first polynomial, then you will not be able to recover this one. But what you could then do is send them this way, and maybe distribute those errors among the Reed-Solomon cohort. And if each Reed-Solomon cohort gets less than 4 errors individually, you're fine. So now a burst of length 6 could be recovered by the interleaved code. Whereas if they were sent individually, you wouldn't be able to. You'd miss one of them, or even longer bursts. It'd be a lot more than maybe even 12. All right, so the last thing I'm going to do, a little quickly, is sort of going to be a shift back to the rational function problem. So in the rational function vector case, the parametric linear system case, one of the assumptions that was made was that the matrix of the system had to be full rank. All right? If the system is rank deficient, you're not able to use the Boyer-Kaltofen algorithm to recover the vector of rational functions. And so this was a problem that I really wanted to solve. And this was, I recognize this as a bracket for the NCAA championship. And the reason I have it here, it was sort of, Capital One had ran this commercial where they said that your bracket is fine, it's just the teams that were off. And in some sense, that is the way you want to look at the rank deficient system.
So maybe not everybody is familiar with this kind of.
Oh,
Could you explain what that is?
So in March, it's called March Madness, a lot of the NCAA basketball teams, these large schools, I don't think CUNY isn't one of them, but NC State is one of them. They're over here, I think. Somewhere over here. And so these people, they decide, based on your record, I think it's about 68 teams. Here it's 64, I think. 64 teams. And they play this knockout competition. That's why it's called March Madness, to see who will be the NCAA champion. And what I guess spectators can do is fill out a bracket where you try to predict which teams will win. I think Berkshire Hathaway, Warren Buffett, offers $1 million to his employees if they can get a perfect bracket. I don't think anyone has ever gotten a perfect bracket. I think the closest was a 5-year-old girl from North Carolina, somehow picking the teams based on their mascots or something. But anyway, this is my bracket. So the green are the ones I got correct, and the red are the ones I got wrong. What I also like about this is that this was the biggest upset in 100 years of the NCAA championship, which I actually predicted correctly, because I didn't know what it was doing. I just was picking based, I think I was looking at rebound stats. But anyway, so this was the bracket challenge, but no one ever gets a perfect bracket. So Capital One was running this ad where they said, well, your bracket is fine, it's just the teams that are off. And it turns out that with the with a linear system model, when you have a rank deficient system, you have two kinds of errors, two distinct kinds of errors. And those errors we'll term matrix errors and right side vector errors. See, when the system is full rank, you can think of all of the errors as being right side vector errors. So you can always say the matrix is fine, it's just the right side vector that's off. Because for every solution, I just have to take A times X, I'll get a right side vector. But that's not true when your system is rank deficient. So to generalize, we'll consider WL to be the set of solutions to our evaluated system, and W hat to be the set of solutions to the hatted systems that you get back from the black box. And an error would mean at xi sub l is if there exists some solution to the original system that is not a solution to the set of Haddon solutions, right? And this can occur in two ways. It could be that giving my A hat and B hat, right, there's a missing W, but no matter how I adjust B hat, it will not, there'll always be some W missing. That there's no right side vector. That's a matrix error. And a right side vector error means given A hat and B hat, maybe there's a W that is missing from W hat. However, if I were to change B hat, if I were to adjust the right side vector, everything will be fine. These two sets will we'll remove the places where the rank drops. So we'll say these two sets are equal. And so it turns out that what we want to first then do is remove these matrix errors, these places where if I adjust the right side vector, it doesn't help me. And this only happens if the null space of A is not contained in the null space of the A hat that you got back.
What is L?
L is a particular evaluation point. Little l, right? Script L?
This L. Yeah, little L, yes.
Yeah, there's a particular evaluation point, xi sub L. Remember you have capital L many evaluations you're going to use. And little l is just one particular one. So it turns out that what this means is that there's some column dependency in A that does not exist in A hat. And we want to do is figure out the places where this occurs. So we define something that we call a non-essential column. And by non-essential column, I mean, so I have a rank deficient system. And imagine that I drop one column and the range remains the same. That's a column I would consider to be a non-essential column, right? So any such column is a non-essential column. So next we define a minimal linearly dependent set, right? And this is a set where if I were to drop just one element from the set will become dependent. Okay, so imagine you have a polynomial, a rank deficient system, and you compute the column echelon form. What we show is that the non-zero entries in the last column are actually the rightmost minimal linearly dependent set of A. Right? Because remember, when you compute that column echelon form, you have the most zeros on top of the rightmost column. And we're saying that those non-zero entries correspond to, in the matrix, the rightmost linear set of columns. So what you were to do, if you were to place the columns into a set from the right side, starting from the right side, until you get a minimal linear dependent set, that is the non-zero entries in this last column of the column echelon form. So remember that, maybe I shouldn't say remember, but because we want to know where these column dependencies don't exist, it is exactly these non-essential columns we sort of want to investigate, right? And what we show is that, well, every non-essential column can be made part of the rightmost minimal linear dependent set by just applying some permutation matrix. right? So what are we saying here is that, well, if there's a certain number of these non-essential columns, there is a permutation matrix I can apply so that every non-essential column is a part of the rightmost minimal linear dependent set. And when you change the columns, you don't change the degree, sorry, you don't change the solution. You just change the order that the solution is in the right side, right? Maybe when you do column interchanges. It's sort of like changing x1 and x2 sort of. So this part, because we're dealing with a polynomial system, we want to bound on the, in some sense, well, it will be a subspace in the null space. We want to bound on how large the the solutions in the null space can be. And the reason for yes,
I'm still not sure about the framework. Let's go back to the previous slide. So these are all columns of polynomials. Is that right?
Yes. Well, actually, well,
are they columns of polynomials?
Well, it depends on where you're looking. Here, these are polynomial scalar. These are scalar columns.
And but the idea of a non-essential column is a column of polynomials.
Well, yeah, or it could be scalars. Well, polynomials are more general, yes.
Right. So why isn't this simply just a linear space rank? Is there something going on using polynomials?
Just evaluation. You can evaluate the polynomial.
The parameter, you mean?
You can plug it in.
Because they're all polynomials in one variable, so
yes.
we have this parameter, but I'm just trying to, what's the space of this? What's the linear space we're talking about?
I'm not sure. So let's say whether we're looking at vector spaces or a field of rational functions. That's what you're asking.
So I'm just trying to.
So since there's some linear algebra going on, you want to know the field, right? The ground field.
Maybe, yeah.
So that's, I guess, depends on the situation. If you don't evaluate the polynomial, the points, so this is the field of rational functions. If you evaluate, that's the field, that's the ground field, that's what
yes.
whatever the field is.
So and we're gonna solve it by evaluating. I mean, it might be possible that you didn't have to. But we're gonna solve the system by evaluating the polynomial. So yes, but there are two views. That's why here, to be careful, you sort of need this bound on this null space of A, because, and the reason for that is I wanna a priori know how many evaluations I'm going to request of the black box, right?
And we don't know the coefficients of the polynomials.
Yes. No, you don't know.
No.
Yeah.
So when you're viewing it as a column of polynomials,
yes.
What's the ground field?
The field of rational functions in U. Like Q of U or C of U, whatever it is. But he doesn't actually view it that way when he computes, because he doesn't know the actual polynomials. So he represents them not as like what we usually do. He represents something else, like some program that computes something about them. Not necessarily the coefficients.
So yes, so the coefficients are unknowns.
Unknown.
Yeah, just some unknowns, and that's where the feed side comes. They're just unknowns, but they're linear in the coefficients. I can then solve for the coefficients using this regular But what I want to do, I want to somehow recover those places where the null space of A is not contained in the null space of the A hats. Or the two null spaces are not the same. And sort of how do I figure that out? So I use this bound. I guess I should skip here. And so I have again these well, I consider polynomials to be in omega because I have this larger degree bound. But it's very similar to what we were doing before with the linear system with a hat and phi. In that sense, so the first thing I will do is solve the homogeneous system in order to recover those places where those columns where there's some linear combination in A that is not in A hat. And it turns out that there's a matrix error at xi sub lambda due to some column discrepancy if and only if when I solve the let me make sure I'm saying this right. Yes, sorry. Yes, when I solve this homogeneous system, I'm saying this right. Yes, so you look at the last column of the column echelon form, right? And you compute the common factors of the last column. The places where they're, the common factors of the last column. So actually, and that makes that a little confusing. So remember, I recover the coefficients, right? So you can think now. So I guess I'm going between two spaces.
And when you do the column echelon form, you're already permuting the columns, right?
Yes.
So we don't know in advance what the last column is. But after you've computed the column echelon form, the last one really represents a particular column in the original. Is that what you're doing? Because you...
Yeah. Well, then it's not a particular column. So...
Because
so once you've evaluated, right, these columns represent the coefficients of a polynomial, right? And what you've done is you've compute the column echelon form. Because it's sort of, you have a null space, and the problem is I cannot pick out the ones that have the error located polynomial. Like I would usually do, right? So you solve this homogeneous system, right? And what you're getting is a subspace of the null space of A, right?
What is the difference with A hat and A again?
So A hat is what I get back from the black box.
By evaluating it, eta, zeta.
Yes.
So see, maybe it makes sense to go back to the very beginning and remind the notation.
Okay.
Let me think about this again. So,
oh yeah. Sorry. This far back. So here. So A hat is, so I have a black box with these linear systems. And here the assumption was that the matrix is full rank. But here now the assumption the matrix is rank efficient, right? And I want to recover the solution f over g, right? As well as the error located polynomial, right? So a hat is a scalar system that I get back from the black box, where most times, if I were to take the evaluated solution, it would, a hat times f would equal g times b. But sometimes that's not the case. When it's rank deficient, now you have a set of solutions.
Who picks xi?
Hmm?
Who picks xi? So the hat depends on xi.
Yes.
So,
So you're allowed to pick that based from field K. You can pick anyone's. Different, that would be distinct though. That's the only criteria there. And so here, and I think I can see sort of where the confusion, I'll try to clear that up, is that, so you have these polynomials, and I'm going to set up this large system based on this many evaluations of the polynomial, right? And what I'll have is these, the coefficients of that system, right, are the coefficients of the polynomials for each of the phi1, phi2, phi3, and so on.
so what is the notation omega? What is this?
So omega is because now I needed more evaluations because I wanted to capture these null space polynomials, which might be larger than my original degree f. Because you can imagine that in the null space, the degree of the polynomials could be larger than the degree of the solution, the null space vectors, the null space polynomials. And I want to pick all my points in the beginning that I'm gonna request from the black box. And here, so what happens is when you solve this large linear system in the coefficients, or here in omega, just like consider these null space vectors, right? I'll get the coefficients of polynomials. So then I can then convert those to actual polynomials in U. And what we show is that if there was an error, if there was a matrix error, then it will show up as a common factor in that last column. And the idea is, well, the idea is you can just permute and get all of the linear, you can find all these minimal linear dependent sets, and then remove all matrix errors. Now, the issue there is that algorithm is actually could be exponential because of the number of minimal linear dependent sets you would have. But I'm of the view that you actually don't need to compute every minimal linearly independent set, because in some sense there's some relationship amongst these minimal sets. And so I propose an algorithm without proof that is actually linear in the size of the matrix. I don't think I describe it here. So then what you do is, so you remove the matrix errors, but then, let's see if that's right. missing something. And, okay. So anyways, you remove all of the matrix errors, right? And then what you can show is that, well, you only have two types of errors: matrix errors or right side vector errors. But then the right side vector errors are exactly those errors that you get when the system was full rank. So if you remove if you remove the matrix errors, then you can then solve for, then you can just solve the system, and you'll get the error locator polynomial as well as the solution. So I guess what is next is sort of to prove that the polynomial algorithm that sort of finds the matrix errors without having to compute all of the minimal linearly dependent sets. The other thing would be nice is to see how the work for the burst errors, how that compares to what is done in information theory. Sort of this view of recovering the polynomials, and then whether you stack or not, how that actually compares to actual burst error correcting codes. And it might also be possible to use error correction as a way to speed algorithms, and I know for multiplying matrices, Daniel Roach sort of applied this idea.
Thank you.